We will now focus our attention on bending in beams. Our aim would be to determine the internal forces within a beam which is subjected to some external loading. Previously, we have discussed structures which were subjected to axial loads, and we tried to determine the internal effects, which we call stresses and strains within a structure. Now, in this new section, we would try to work out internal forces within a beam. Our broader objective of this topic is to determine the stresses in members which are subjected to bending. We will first try to establish the shear and moment diagrams for beams. These diagrams would provide a useful means for determining the largest bending moment and shear within a member. After that, using these internal forces, we will work out the stresses developing within the member. Before getting deeper into bending moment and shear force diagrams, let us remind ourselves what are beams. Beams are slender members which are unidimensional, and they are subjected to loads that are perpendicular to their longitudinal axis. So the axis which is along the length, that is called longitudinal axis, and loads are applied perpendicular to the longitudinal axis. Beams can have different types of supports, such as simple supports, which involves a pin connection on one end and a roller connection on the other. Beam can have a fixed support only at one end, and those are called as cantilever beams. We can have same pin support, but on one end, which is overhanging. These are called overhanging beams. So the main idea is that we are not always able to provide simple supports which are most economical, and mostly they are the preferred support. We might end up with different types of support depending on ground conditions. From our statics knowledge, we know that whenever some load is applied onto the beam, that load is then transferred to the support. And the way we transfer it to the support is by using equilibrium, especially if we have a determinate structure. In other words, if we are able to get our unknown reactions from the available equilibrium equations. Normally, the equilibrium equations are summation of all the moment must be equal to zero, and summation of all the forces must be equal to zero. So if these two sets of equations give us sufficient equations to solve the unknown reactions, then we call those structures as determinate structures. In this course, we will mostly be considering determinate structures. So from our statics, we determine the reactions, unknown reactions of these determinate structures using simple equilibrium equations. We didn't handle the internal deformation of structures. In mechanics of solids, we are mainly concerned with the internal deformations. So after working out the reactions, the next step is to determine the internal forces developed. We will now consider how these internal forces are developed in beams and how they can be quantified. In the case of beams, the external loads produce two internal effects. One is called bending moment and another one is called shear force. The bending moment is defined as the summation of moments about the centroidal axis of any selected section of all the loads acting either to the left or to the right side of the section. So imagine if we have a cantilever beam and that is subjected to some loading. In this picture, we have shown the beam at an exaggerated depth because we want to find out the forces within the fibers of this beam. The cross section of this beam is considered rectangular, as we can see over here. This rectangular section has got a centroid which is shown with the dotted line. This centroid is constant throughout the length of the beam. The beam considered is cantilever, and we assume that the beam is made up of infinite longitudinal fibers. So the red lines which we have drawn, they are showing the longitudinal fibers. Also, we assume that the whole length of the beam is sliced into green sections. These are infinite in numbers. So essentially, we have divided the beam into infinite small boxes. From our knowledge of mechanics, we can appreciate that at every green section or at every vertical green section, we have some bending moment getting developed. At the point of application of the load, there is no bending moment because the force has got no lever arm. But as we start moving slightly to the left, we start getting bending moments within the beam. The magnitude of the moment is maximum at the root of the cantilever because the applied load time the lever arm is maximum. So please note that the load magnitude doesn't change. It is because of the lever arm that our moment magnitude is changing. As we know that moment is made up of load time the lever arm. So the load is constant, but as we move towards the root, lever arm increases, and that correspondingly increase our moment. So collecting all of these moments at different cross section, we get a linear distribution of bending moment. Please note that at the root of the cantilever, the moment is maximum. At the point where we have applied the load, moment is zero. And as we start moving towards the support, we start getting moments, and that moments is increasing linearly. We will discuss later why this is linear, but one thing can be conceptually appreciated that there is an increase in the moment. We can also conceptualize that the bending within the beam cause tension in some fibers and compression in the other fibers. Thus, the fibers which are above the neutral axis, which we called as centroidal axis, they are all in tension, and the fibers below the neutral axis are all in compression. So all these red fibers, which are located above the centroidal or neutral axis, have got some tensile force running in them. Similarly, the fibers which are below the neutral axis or centroidal axis have got some compression force running in them. We can see that at the neutral or centroidal axis, the force is zero. So the fiber which is at the neutral axis or the centroidal axis that has got no force. This can be appreciated by our thought experiment. As we know, the top fiber under the available loading and support condition is in tension, and the bottom fiber is in compression. So it is obvious that some fibers are in tension and some fibers are in compression. Thus, we can say that the fibers at the top of the beam are having maximum tension. And then as we start coming down the depth of the beam, the tension starts reducing. And there should be a point where the tension force becomes zero. And then after that, compression taking over. The fibers start getting compressed. And as we come to the bottom of the cross section, we get maximum compression force. The point where we have got zero force in the fiber, that is called neutral axis. Later we will prove that the neutral axis and the centroidal axis for a rectangular cross section is the same. In this figure, we have highlighted the tensile region in yellow and the compression region in green. As we said that there are infinite fibers above the neutral axis and all of them have got some tensile force. So we can find the resultant of all these forces which are above the neutral axis. And the resultant comes out to be as T. We can do the same exercise with the fibers which are below the neutral axis and finding out the resultant of all the compressive forces, we get another resultant which is C. Now, using equilibrium, we must be able to appreciate that tension has to be equal to compression to avoid any imbalance in the load. Thus, the tension has to balance out the compression C in order to ensure that summation of all the forces in the horizontal direction is zero. Therefore, we can say that T is equal to C. If we call the distance between the resultant T and resultant C as D perpendicular, then we can find the moment at a particular cross section as T time D perpendicular or C time D perpendicular. So the moment is actually the internal moment within any cross section which is shown in green. So the vertical green lines, they are giving us cross sections. And this moment is a moment at any cross section between the point of application of the load and the support. So externally, as we discussed, we have got the moment diagram which looks like this. Externally, the moment is equal to force times the distance d. That external moment must be equal to the internal moment which is shown over here. Again, the external moment is equal to internal moment in order to ensure the equilibrium. We are not considering any accelerations in this structure. This structure is purely in the state of statics. Another way looking at this problem is that we have an external moment at a particular section, which is the applied load times the distance from the point of application of the load to the reference cross section. That moment then is decomposed into tension and compression by dividing that moment by the lever arm, D perpendicular, and then the tensions and compression, they get decomposed into different forces that are applied onto the fibers. Please note that the lever arm between P and C can easily be found if we know the overall depth of the cross section. In the case of lever arm, we need the distance of the neutral axis or the centroidal axis, which is known in the case of rectangular cross section as the centroidal axis is in the middle of the depth, and the distance of T and C from the top and bottom fiber respectively can be found from statics. After that, using some algebra, we can work out the lever arm. We have established how the external moment generate an internal bending moment. We have discussed how the moments are generated within the beam, or in other words, due to the application of loads that are perpendicular to the longitudinal axis, we can have internal moments developing within the cross sections of the beam. Now let us discuss how these moments will create shear forces within the beam. The moments and the shear force, they are the internal effects. So if we cut the beam anywhere within the length of the beam, at any cross section, we will get a moment and a shear force. This is similar to what we have already done in the case of axial forces. We discussed that if a structure is subjected to set of loading and we cut that structure, we will get internal forces which might be aimed in an outward drawn normal to the cross section or might be lying within the cross section. The one which are in outward drawn normal, they cause axial stresses. The one which are parallel to the cross section, they cause shear. Similarly, if we cut a beam, we get an internal moment and a shear. This internal moment can be further decomposed into tension and compression. So at a particular point within a cross section, we can have a shear and an axial force, which can be either tension or compression. Shear force is actually the vertical force that exists within our cross sections. In our beam, as we said, we have got infinite cross sections, which are shown by these green lines. At every cross section, we can have some shear force getting generated. These shear force are generated by these moments. In order to justify this statement, let us consider two sections within this beam. These sections are called as section 1 and 2, and they are separated by some distance. We can see that at section 1, moment is bigger than at section 2. And the reason is that at section 1, the lever arm is bigger as compared to section 2. So we can easily write M1 is greater than M2. Now we can decouple this moment by dividing it by the lever arm. As we said that the lever arm is constant throughout the length, that would give us the resultant tension or compression at section 1, which will be greater than the resultant tension and compression at section 2. So at the top of the beam above neutral axis, the T1 at 1 will be greater than T at 2, and below the neutral axis, C at 1 will be greater than C at 2. Now again, the T at 1s and C at T1s, they can be decomposed into the corresponding forces as shown. So at section 1, for all these fibers which are above the neutral axis, we can have the T distributed. Similarly, at the bottom fibers, we can have C broken down corresponding to each and every fiber. Now imagine we pick one point which we call 1, or this is just randomly a fiber which is chosen. The fiber is located above the neutral axis, so this fiber would be in tension and there would be some tension force on this fiber. We call that tension force as T1. So the fiber would have a tension force T1 at section 1, and at section 2, the same fiber would have tension force T2. So imagine we have chosen this area. In this area, at particular fiber location, we have a T1, and at section 2, we have force T2 in this fiber. Please remember that T1 is bigger than T2. So that means to say their T1 minus T2 is a force that can cause imbalance within a particular element. As we have divided the whole beam into infinite number of elements, we try to isolate this element at the reference fiber location. So we have got this element, and this element at the top has got a fiber whose tensile force is T1 at section 1 and T2 at section 2. We have established that T1 is greater than T2. So there is an imbalance of T1 minus T2. This imbalance can spoil our equilibrium status. In order to avoid that, we have to put an equal and opposite force T1 minus T2 below our reference element. These two forces, which are equal and they have got some lever arm, they are able to cause a moment which is in counterclockwise direction. In order to overcome this moment, we have to provide another moment which is in clockwise direction. So essentially, this shaded part, which is isolated as a free body, has been equilibrated. For this shaded part, we have summation of all the forces equal to zero and summation of all the moment equal to zero. The vertical force, which we have shown over here, this vertical force is called shear force. Since this vertical force is applied on this small element, so this is only a small piece of the overall vertical force within the cross section. Please note that we can do the same exercise with any element which is below the neutral axis. In case of this any element which is between section 1 and 2, we have again C1 and C2 appearing below at this layer. C1 and C2 are the compression forces within the reference fiber which we have considered below the neutral axis. As we said that M1 is greater than M2, so is C1 greater than C2. Thus, C1 minus C2 cause an imbalance force which is C1 minus C2, shown by this red arrow. This force has to be balanced out by another force that is equal and opposite. Thus, summation of forces in horizontal direction is satisfied. But these two forces which are equal and opposite, and they are at some perpendicular distance from each other, will cause a moment. And that moment has to be resisted by a clockwise moment, which is shown over here. And again, we have at this point a vertical load. Thus, for all these boxes, we would have small vertical loads appearing. And once we add all of them, we will get the resultant shear force at a particular cross section.